Very grateful to Jürgen for inviting me here. And I'm very glad to see that people here begin to appreciate the fundamental importance of recurrent neural networks trained by backpropagation or gradients. Because this is a very complicated subject, I don't think I can cover so many topics as Jürgen just did. That was amazing. I will not even try to get into so many details. It is a large topic, however. At this website, I have posted many papers which give details just as complex as what you've just heard from Jürgen. And if I say something outrageous, go to this website and there will be more details. The main thing I want to talk about today is something new. Just last week, we published a new paper which gives a strong indication that the brain itself uses recurrent neural networks trained by modulated backpropagation to learn to predict its world. That's a very controversial statement I just made. Many people would say you're crazy, but people have told me I'm crazy my whole life. When I first started doing backpropagation in the 60s and the 70s, everybody said, you must be a crackpot, this is impossible. So people will still say it. In the field of computational neuroscience, many people believe that the neural networks we are working on have nothing to do with the real brain. They will tell you there are two kinds of mathematical neural network designs. There are the artificial designs which work in engineering, like ours, and then there are biological neural networks which have no clocks, which are spiking neurons or differential equation neurons with Hebbian learning, and they say, of course the brain does this. There are huge funding programs in governments trying to buy computer machinery based on the so-called biological neural networks. And this has presented a great problem for industry. Do they want to spend money on things which do not work? This has become a big issue. I wish I had time to talk about it. It's been funny to observe these collisions. But this is an article of religion among many modelers. This is not real neuroscience. There is a part of neuroscience called systems neuroscience, which is different from the people doing the mathematical modeling. And many people in systems neuroscience will tell you, of course we know there are clocks in the brain. Of course we know that these simple Hebbian models are not the whole story. Given all this religious debate, I decided to do an empirical test. Let's look at the very best real-time data on the higher centers of the brain, and let's do a test of their hypothesis of asynchronous neural nets and my hypothesis of recurrent networks trained by backpropagation. And the empirical data strongly support the backpropagation theory of what the brain does. So now, how do I explain all that? I've already used 5 minutes. God help us. Okay. So I'm saying that the brain does deep learning. And I guess we all have different views of what is deep learning and even of the history. I like what LeCun says. He says that deep learning is really the second rebirth of the neural network field. The first rebirth of the neural network field was back in 1987. Before 1987, they called us all crazy. They wouldn't believe it. By 1987, the success of backpropagation became well known, and the field crystallized with large meetings. But even so, computer science did not accept it. Many people in industry used neural networks from 87 till 5 years ago. Industry has been using large-scale neural networks with deep learning much more than most of the world knows. Industry did not advertise its success. Computer science has done a much better job of communicating its success. But these networks were already useful long before the great work by Andrew Ng and Jan LeCun, which started this whole new avalanche of applications. That project by Ng and LeCun did not really invent new neural networks. It was a kind of application testing project using neural network designs they already knew to challenge major application challenges in computer science. It was the empirical success of these methods on large problems which woke up the world. And let me say a little bit more about it. That grant, that project by Ng and LeCun, was something I funded from NSF. I funded it with this program at NSF called COPEN. If you go to the NSF webpage, Cognitive Optimization and Prediction with Neural Networks. Actually, this slide was something I developed for workshops in China. People in China asked me, what are the really promising new directions for research in neural networks? I said there are 5 directions. For each direction, I have an arrow. That's a direction. It's a vector. And there is the development of mathematics for universal learning to predict, universal brain-like learning to optimize. You could call it reinforcement learning. And then there are certain applications. At NSF, I persuaded the whole agency that we needed a new funding effort to combine artificial neural nets and biological and psychology research, to bring these disciplines together, to learn from each other. So the challenge is build neural network designs which are useful in engineering, unlike some of these spiking designs. Come up with designs that are useful in engineering, but also which we can use to help explain the brain. I believe that this funding program was much better conceived than these crazy big brain projects I hear about that are implementing Hebbian learning for $1 billion. I mean, that's just crazy. But this project, it was small, but what it produced for a small amount of money was very exciting. And one of the things it produced, it allowed Ng and LeCun to do what they had wanted to do for years. It provided the funding to make it possible to challenge initially 7 major benchmark challenges. Each one of these had a history going back decades and decades. People in traditional computer science did not want to believe in deep learning because they did not want to believe they had wasted 20, 30 years coming up with very narrow specific designs for each of these problems. In comes a neural network and does better in 1 year with the same design applied to 7 problems. This was a fantastic success. This was the real birth of the deep learning movement as we know it today. This success also led, it didn't change the minds of the computer scientists, though. They're still very conservative. But then came DARPA. And DARPA wanted results. And they looked at these results and they said, hey, we'll give you some more money. We have problems that need attacking. And then Google became interested. And then it became an avalanche. And once Google and DARPA were funding it, after a while, computer science really started paying attention. And then they said, oh, that was part of our field all along. That's the history of these things. So that was where deep learning comes from. And this is maybe an example of the most famous deep learning thing out there right now, Google's TensorFlow. I have heard people in Washington, D.C. talk about Google TensorFlow every day of the week. It's become a huge fad. Everybody knows about it. Kids next door know about Google TensorFlow. And if you go to their webpage, at the core of it, it's all gradient-based learning. Okay? It's gradient-based learning, which I would call backpropagation. At least if you have correct derivatives, I call it backpropagation. If you invent the derivatives randomly, well, that's something else. So, now the interesting question is, why didn't people realize how to do this long, long ago? When I was in graduate school, people said neural networks are totally crazy, they can never work, and you must be a crackpot. You are a heretic. And the reason it cannot work is that we all know the great work of the great hero of artificial intelligence, Marvin Minsky. And Marvin Minsky with Papert wrote a book called Perceptrons, which became a kind of a new Bible. And to this day, many people still revere Minsky for his deep insight in his book, where he said this was impossible. And he is still revered for that insight that neural nets are impossible. And he said it was impossible, giving this example of a simple learning problem where you have just two inputs. This is your desired output, and you only have 4 data points, and you try to learn the mapping. And he said nobody in the world knows how to train a neural network to solve even this simple mapping problem. Of course, people knew about gradient descent. Why didn't they apply it? There was a paper by Sunichi Amari where he said we could consider doing steepest descent on this. But of course, it would not work. And that was the end of it. That was what Amari did. And the reason why this was considered a showstopper, there were 2 reasons. One reason was no one knew how to calculate the derivatives efficiently in a local brain-like fashion. They just didn't know how to calculate the derivatives. And the other thing is, the kind of neuron model which was popular at the time was like a spiking neuron model, 0 and 1 outputs. People said the brain is like a modern digital computer, so of course it must be digital. It must have outputs, 0 and 1. This was an article of religion, of ideology. Everybody knew that neurons output 0s and 1s. People still know crazy things today. And I'm still a heretic. I don't believe these crazy things. So they believed the neuron output 1 and 0. In 1971, I went to Marvin Minsky and I said, I have a solution to this problem with neural networks. In 1971, this is documented. And Minsky said, I do not want to be co-author of a paper on this new method. Minsky could have shared credit for backpropagation. He said, I don't want to do it because those neuron modelers, they have so much power in science. They will laugh me out of court. I will lose my standing at MIT. I cannot afford to take such a risk because everyone knows that neurons are 0, 1 output spiking neurons. Many people still know that. So I showed Minsky this data. This is exactly what I showed him in 1971. This comes from a book by Rosenblith. And this is real-time series of higher order neurons in the brain. And I said, you know, if you look at this, does this look like square waves? Does this look totally asynchronous? At the time, the people who studied real neuroscience said what we have are a series of volleys. Now they call it bursts. I said, if you want a correct model of the neuron, shouldn't you look at data on the neuron? Are we making up models out of metaphysics? Where do our models come from? Let's look at data. And if we look at the data, what we see is basically a regular clock cycle. And at every sample time, there's a continuous variable. What is the intensity of the volley? And I said a correct model of the neuron should not be continuous time. It's discrete time. There is a clock here. And every time cycle, what you have is not a 0 or a 1. You have a continuous variable. Now, it turns out neurons haven't changed since the 1960s. Neuroscience has changed, but if you're interested, there is a textbook by Mark Baer and Connors and someone else. It's one of the best books you can get if you want to learn a little bit quick about neuroscience. I strongly advise spending $35 at Amazon for this beautiful, up-to-date color book by Baer and Connors. And if you look in that book, you'll see that even to this day, we know there are bursts in the higher level cells of the cortex. This is still an applicable model. So now, moving on, the question was how to compute the derivatives. And the truth is, many papers in the literature today do not calculate derivatives correctly, because they're written by people who say, hey, I know what is a gradient, I took first-year calculus, and then here's how I get my derivatives. And with complex nonlinear systems, it doesn't work. There are several types of derivatives. It is very easy to get the calculation wrong. To get it right, it is very important for you to know what backpropagation really is. And what backpropagation really is the chain rule for ordered derivatives. This is a specific type of derivative. This is the kind of gradient we need to train neural networks correctly. It turns out this is a universal method for any differentiable system, feed-forward. And what's more, and this was in my thesis in '74 and on my webpage and so on, the other thing is that you can apply the chain rule for ordered derivatives directly to dynamic systems with time lags. The first application of backpropagation through time was actually to a large-scale econometric package. And it was in use in general-purpose econometric software in 1974. People have gotten Nobel Prizes from using that software, all based on backpropagation through time. Oh, it is so painful to go through this. This slide deserves an hour in itself. This is a big part of this whole conference. Jürgen talked about many of the critical details here. But let me just talk about some general things. There's a general family of neural networks, which I call time-lag recurrent networks, and you have a one-period clock delay. This is what the classic biomodelers hate, but in fact, this is what you need in econometrics. This is what you need in statistics if you want good, consistent statistics. It can be shown that this general class of neural networks, which includes LSTM, this general class of neural networks is a generalization and approximation of something called NARMAX in statistics. It's basically the most universal learning machine you can put together for prediction. And people like Ford Motor Company and Siemens achieved breakthrough performance using this long before the new wave of deep learning. There were people saying, I will never see a neural network doing anything in the real world, driving cars controlled by a time-lag recurrent network. They didn't know what was hidden in their car, and Ford didn't want to show it in their face. But the problem with backpropagation through time is it's not real time. There is a real-time method which I developed. There are other competing methods, but there's a method which I developed called the error critic, which overcomes the complexity problems that earlier methods had. It is described in detail in chapter 13 of the Handbook of Intelligent Control, and that's posted on my website. That gives you the exact details of how to do it. People at Ford tried it. They said, it works. You can use backpropagation in real time to train time-lag recurrent networks. They have done it. It works. But they don't use it much because they do offline. Offline is good enough for Ford usually. There's another kind of recurrence. It's very important to understand the difference between time-lag recurrence, which is essential to high-quality forecasts, and simultaneous recurrence, which is essential to mapping capability. Long ago, for example, in a paper by with Illen and some earlier work, we gave an example of a simple function mapping problem which feed-forward convolutional networks cannot learn. You put this mapping, it has to do with robot navigation. You take this mapping and you try to learn it with convolutional neural networks, they cannot learn it. There are intrinsic problems in the function approximation capabilities of the ordinary convolutional networks. But if you wrap around this recurrence, a high-speed simultaneous recurrence, similar to what people want to do with Hebbian networks, except here we train them to make them work, okay? With that kind of fast convergence, we were able to prove accuracy in some applications. So my claim is the brain has to combine all of the powers. It must combine complex mapping and ability to predict the future. Not to mention, so the theory I published long ago in many places, based on, I wish I could talk about these people, great neuroscientists, Nicolelis, Richmond, is that the brain learns to predict. This is one of its fundamental principles. Inputs come to a place called the thalamus. There is a corticothalamic loop, which is highly nonlinear, and it learns to predict the future of this. There are people in systems neuroscience who talk a lot about that. If you look at the actual wiring of the cortex, a lot of people talk about cortical computing. Most of them don't show you pictures of the cortex. Now, Grossberg does, but he doesn't do learning so much. So this is a picture of the giant pyramid cells, which are the real backbone of the brain. We have known for years that there are clock inputs which come to these cells from a place called the nonspecific thalamus. And for years I've argued this is how the brain works. But it has clocks, and some people don't like that kind of model. So what I've done this year, there is a new paper. It's an open access paper. You can find the link on my webpage. Just last week, it came out from Frontiers in Systems Neuroscience, where I actually went in and did this empirical test I talked about in the beginning. And basically, I wish there were time to elaborate. This is just giving, we did something like 10 statistical measures. There's a lot more work to be done with this data. I really hope somebody does a time series data competition with this data, because this is really important to understanding the brain and the mind. Okay, it's really important data. And basically, we used a statistic called the inversion number to compare the classical hypothesis versus the backpropagation alternating cycles, and we got 40% less error. Data supports our theory. My final slide, I wish I had time to talk about applications the way Jürgen did. There have been many exciting applications you haven't heard of in the engineering field, in the industry field, but there are also huge risks and opportunities. The dangers in this field and the opportunities in this field are much, much larger than any of you have heard. It's a huge topic. People at NATO asked me to give a talk on that, and I have a book chapter in press, natoterrorism.pdf, which talks in great detail about amazing, scary things that could really happen and amazing good things. And I hope you would find that chapter interesting. Thank you for your patience.